Good morning, everybody. As usual, we have our Wednesday seminar on AI and machine learning. And today we have the pleasure to host the Philab team, so Pierre-Philippe and his team at ESA. And Philab mission is to accelerate future Earth observations, especially looking to innovative ways to accelerate it. And Pierre-Philippe promised to challenge us today, so we are very happy. And I think we will have a short introduction from Pierre-Philippe, and then a showcase, to overview also as showcases from the ESA experience. So there will be several people presenting, so you can see the names into the screen, and we will have time at the end to wrap up and to have a few questions from the audience. So thank you so much, and Pierre, floor is yours.
So many thanks, Paolo. Many thanks also for the invitation. It's always a pleasure to be able to share what we are doing and also our passion and excitement for new technology. So today I will focus on AI and how it applies to Earth observation. And I start with this beautiful slide being how a machine would see Sentinel-1 with a Van Gogh style, and I'll come back to this technology. I can move. Yeah, so you know that AI is basically getting everywhere, from self-driving cars to gaming. It has breakthrough in natural language processing, computer vision. And what we try to do at the lab is to bring this technology to the world of Earth observation, which has some specificity. And the reason we do this now is that because there is a kind of convergence of three things that makes this AI not a hype, but a very impactful technology. First of all, big data and open data. I will talk mainly here about data observing the planets. The fact that the computing, thanks to the Moore law, has become extremely powerful and also very cheap, and the ability to have a variety of algorithms that can train on this data. So the reason why AI matters, according to us, is really because not of the intelligence, which, by the way, we cannot define properly, but because it has the ability to create a software automatically, in particular for problems you don't fully understand. So this is a kind of coding machine for us that is fed by big data, and that creates the magic. But I want to repeat that AI is just a tool. What we try to understand is this beautiful planet here, and we want to give the information to decision maker in the way that they can act on it in order to move towards sustainability. So our job in ESA is to launch missions, but also to try to turn this data into information that can be used by these decision makers. So the challenge is to bring all these pieces of the jigsaw together. So I'll go to the three elements that makes the AI revolution. First, the data. I mean, you are quite familiar with this, but there are new actors like new space with small satellites, also HAPS, which are drones that can stay there for a long time. IoT is coming strongly to our field, so we need to merge this geospatial data with billions of little sensors. And this is the big challenge, in fact, to have this macroscope by fusing this data. And AI is a technology that enables this at scale. Just a few reminders here about the beautiful the power of Copernicus to see, for example, disaster or natural processes like volcanic eruption in different frequencies, from optical to radar, atmospheric chemistry. So you have all these pieces of the jigsaw together, and you can turn them into also actionable information with Copernicus services. Then you have the new space bringing a very high resolution to this. And this is really the challenge, to fuse these different scale in time, etc. And ESA is moving on this by creating a new category of mission called the Scouts. You see the two first examples here, mainly linked to atmospheric chemistry and hydrology. So just to summarize our problem or challenge, we have all these pieces of information, different type of sampling, different type of error, and we need to make sense of it. And this technology enables this because it learns from this data and can go and mine this data to get the real information. The other piece of the element, I won't dwell on it because we will talk about it in the talk, is the computing, the evolution through the Moore's law, making it extremely powerful, but also creating chips that are dedicated to AI, like accelerators that are very low energy and that can go on a satellite. So what we try to do at the Phi Lab is to look at the strengths of these different type of computing, from GPU, TPU, VPU, HPC, all acronyms, but also neuromorphic, and we will talk about later, and quantum computing. Regarding algorithm, AI is a big family and we focus mainly on deep learning. This has been the big bang since 2012. There is a lot of algorithm out there to classify cats and dogs, and we try to use this to classify images of our satellites by retraining these algorithms. So we start from pre-train, and the trick is to build the data cube on the left side so that it can enter these pipelines of machine learning. So there is a lot of work there. I would even say the majority of the work is in building the data set for geospatial. But once you have done that, you can really easily and automatically extract information. However, you still need domain experts to interpret this because correlation can be obtained very easily, but maybe it doesn't mean anything. So that we shouldn't forget that at all. And the next step is to bring this in the context of the digital twin. You are part of the Destiny initiative. The key there is really to bring the knowledge of the physics, the models, through synthetic data reanalysis, and get the AI to train on it and merge with observation to get the most comprehensive picture of the Earth, but also forecast of the Earth. And that means that the whole value chain of what we have been doing for decades is changing, because the pipeline now is really about preparing the data, augmenting them to enter the pipeline, then creating an app stores of a dedicated task of the ML, and then deploying it for inference. And you can also deploy it on the satellite. I'll come back to that. By building this data cube, there is also a new interaction between science and machine learning, in fact, very iterative, called the force paradigm, where we can extract patterns that the human eye cannot see. And this creates very exciting science. Again, we will talk about this later. One very strong aspect of the machine learning is its ability to transfer the learning, because the paradigm is about learning from data. So you can learn on a drone and move this learning to a satellite. And we are doing this with the World Food Programme, with crop detection in Malawi. And we start from the mapping of cats and dogs, and then get a few more layers to train for the drones, and it works. So this is really this versatility, which is impressive. The technology has also the ability to enhance the resolution of the sensors with some drawbacks called hallucination, and Gervin will talk about this. It has the ability to approximate a state-of-the-art model, like here, radiative models, and we have applied, for example, to the Sentinel-5P radiative transfer model, and it works very well. It creates a very light model that can be reused for benchmarking or for having ensemble simulation. It can also approximate much more complex models like prediction of rain models. And here we have been training with FDL the model on the reanalysis. So it was learning from the physics through this training. And the team has been able to go directly from top of the atmosphere radiance to a prediction of rain with a very good and robust accuracy. This means that you have a huge retrieval chain that is captured by the machine learning. And you could imagine the next generation of mission, that's where the challenge comes in, that gets this top of the atmosphere radiance and directly beam the prediction forecast to the user. Another aspect, which is a frontier, is the unsupervised learning, and Michael will talk about this later. So the machine could see the Sentinel data just as what they call embeddings, which is a view of the machine coding the information so that it naturally clusters in the different properties like crops, land classes, etc. Extremely interesting and powerful approach. And what I wanted to stress also is this ability, thanks to the computing, to move this technology at the edge directly on the satellite so that you can now retrieve information and possibly launch it, download it to the user. So this is new because a few years ago, the computers needed to be radiation tolerant, etc. We have demonstrated with VSAT-1 that you can put off-the-shelf chip like the Myriad 2 directly on the CubeSat. It works. You can deploy machine learning, in this case for cloud detection, so that we can discard intelligently data. But this means that this is the opening of AI in space. And the question is, what's next? And again, the team of FDL have developed a variety of algorithms, one on flood detection here in 2020 that was published in Nature. And it was launched on this mission a few months ago called WildRide, which is a deployer of CubeSat. And one of the U in the CubeSat is in fact a supercomputer with hybrid computing. And the algorithm has been operated there. So it means that you can upload now pieces of algorithm on a supercomputer that can then deploy it, use the data on board, and work with this. So again, this is the opening of, let's say, a kind of apps or app store in space where you could reprogram your satellite according to the application you want, etc. So this is very exciting. So exciting that we want to build a cloud in space to complement the edge computing as a backbone, if you want, that can help in exploration autonomy. And to gather ideas of this, we have launched a call here where I invite you, that is also part of the challenge, to send your idea maybe for the next generation of meteorological mission. And we will select 10 studies of 100K. So the call is still open. So just go there on ideas.esat.int and be as creative as you want. Space is the only limit, but there is clearly a big opportunity in using a kind of algorithm or software-defined approach to the sensor, and that's what we're after. And I'll stop here and thank you very much and pass the ball to Gervan so that the team can give you more technical details on this.
Okay, I think I can start. I am Dario Spiller, a postdoc research fellow from a joint program of Italian Space Agency and European Space Agency, in particular with the PhilAb. And I will be talking about the usage of hyperspectral data for wildfire detection in particular. I don't think there will be the slides about crop type. What we have done so far is that we have explored the data coming from the PRISMA hyperspectral mission, which is a quite innovative mission, carrying on board this hyperspectral camera. And we have started analyzing the potentialities of PRISMA by looking at wildfires. As you can see on the right, we have started the analysis by looking at an image taken in Australia in late 2019. And the goal of this activity is both to carry out a segmentation analysis by using AI, but also carrying out a kind of estimation of the temperature for the active fire pixels. So please bear with me, okay? So for the first analysis, we have analyzed the image, starting from the RGB composite, but then going on with the much deeper analysis, for instance, by looking at the false color composites or the hyperspectral indices. As you can see, there are here at least 2 big wildfires, and we decided to explore the informative content of this image by developing a one-dimensional convolutional neural network. So just by exploring the spectral content of the Prisma data cube. And we have introduced 5 different classes. And once the model was trained in one of this wildfire, we test the model also in the other wildfires. You see here the segmentation maps for the 2 bigger wildfire, and the results were pretty good indeed. So we will continue this analysis, also trying to transfer this knowledge in other areas of the world. We have another image, for instance, captured in Oregon. So we will also test the capability to transfer this learning ability from one area to other ones. So we will continue exploring in this direction. And then in the next slide, please. Thank you. As I said at the beginning, we also explored the possibility to use the informative content along the spectral direction to extract the information about the temperature of the active fire present in the image. To do that, we have used a linear mixture model. That is that we look at the pixel as the summation of different signals. So partly for the active fire pixels, there is the content information from the fire itself, and then there is the background information. And what we want to do is to extrapolate some information from this representation, that is the percentage of the active fire in the pixel and the temperature itself of the pixel. We are working in this direction. We already have good results, and we are working right now in the verification of the results. I mean, comparing this to other sources of information to estimate the goodness of the results. Yeah, that's it. Thank you.
Hello, is my audio coming through okay? Okay, I'm James Wheeler, and as well as working with Dario on the hyperspectral fire detection, I'm also working on synthetic aperture radar using Sentinel-1, and using as many aspects of that to map burned area. So this is more about mapping the extent and the intensity, let's say, of a burn event. It's one of these capacity building projects that we work on in FELAB. And this means for me using 2 legacy tools from that have been developed in FELAB and continue to be developed. One of them is the OpenSAR toolkit. So this is enabling me to process a lot of Sentinel-1 data, and all the aspects of Sentinel-1 that are contributing to detecting burned areas. So first of all, the backscatter, which is showing the intensity of the reflected signal in the 2 polarizations that come from Sentinel-1. Secondly, the interferometric coherence, which is telling you about the stability of the signal more or less between image pairs, and then the decomposition of the polarimetric channels, which tells you about the scattering mechanisms that are in place on the ground. So with all of these 3 aspects, you get a lot of information about fires. Different fires can appear differently especially in different types of vegetation. And the reason I'm doing this is because there's a lack of a training and testing data set for applying deep learning models to Sentinel-1, and a lot of this data therefore is being not appropriately used when it could be in these increasing wildfires that we're seeing around the world. So the idea is to build a large data set. It's appropriately sampled by biome, by fire intensity or burn severity and burn frequency, as well as season, at 5 by 5 kilometer, which is more or less 250 by 250 pixels of Sentinel-1, and including these representative features, and make it available to both the AI community and the burned area community. Next slide. So the second tool is one which is also been developed by Alistair Francis here and former trainee John Mercer-Claude, called IRIS, which is a tool for quick labeling of, first of all, Sentinel-2, but in this instance, it's data stacks of Sentinel-1 appropriately presented, so we can see how the fire is changing in before and after images. We're also looking at high-resolution imagery of the scene to see the land cover, as well as before and after images from Sentinel-2. And the idea is to produce as many of these as possible. And that way, if you are looking to map burned area in your region, you select the most appropriate training and testing samples to apply then your algorithm on. As well as that, you'll have the tools to build your own training and testing data set where we perhaps haven't filled in those gaps. So for me, I'm looking at Mediterranean area in Europe, which you can see the sample sites a little bit fuzzily there on the left. The sort of red dots around that show the density of sampling. And you can see on the right where I haven't been working, but where we're using exactly the same parameters to select the sample sites. You can see there's a huge amount of fire in Africa that will take a lot of effort for people to create such appropriate training and testing. So the pipeline is very close to completion. I've started preparing the Sentinel-1 data, and the next step is to produce these labeled data sets, and following that, provide it to the community. Thank you.
Hello everyone, my name is Andreas Stockholm. I'm a PhD student at the PhilAb and at the Technical University of Denmark at DTU Space, the National Space Institute. Together with Andrzej Kucik and Nicolas Longipé and the Danish Meteorological Institute, we are working on Earth observation and artificial intelligence for automatically mapping sea ice in the Arctic. So to prevent the next Titanic, vessels in the Arctic are utilizing a chart or a map of the local sea ice conditions in the region. And these charts are created daily due to the constant movement of sea ice. And for the past 50 years, these charts have been hand-drawn by professional ice analysts at the Danish Meteorological Institute. This is time-consuming and labor-intensive, and we're trying to automate this production chain. So sea ice charting is often carried out using synthetic aperture radar due to its ability to work independently of sunlight, which is very beneficial in the dark north. It is able to see through clouds, and it still has a relatively high pixel resolution. Unfortunately, it also has some drawbacks, and that is that the SAR texture is difficult to interpret for untrained eyes, and it's very reliant on the surface properties of what it's measuring. And this can contain some ambiguous textures where it's difficult to distinguish between sea ice and open water. So for this task, we're using the convolutional neural network architecture unit to do supervised segmentation to map SAR data to the operational sea ice charts. We have a large open source dataset with more than 400 scenes containing both SAR and labeled data. Next slide, please. So another approach that we are investigating is utilizing generative adversarial networks to do unsupervised or semi-supervised segmentation to convert the SAR style image to a sea ice chart style, similar to converting a horse into a zebra. And using this semi-supervised approach, we hope to extrapolate our model's capabilities of mapping sea ice around Greenland to the rest of the Arctic. And creating daily and high-resolution maps of the sea ice in the Arctic may help make the trade routes, such as the northern trade route from the Pacific to the Atlantic Ocean, through the Arctic more reliable. Thank you.
Hello, everyone. I'm Jamila Miftal, and I'm a research fellow at the PhilLab. And today I'm going to be speaking about the detection of floating objects on water bodies using Sentinel-2 data. So we know that the ocean pollution is increasing, and it is a threat not only to the marine life, but also to us as human beings. The goal of our project is to construct a large-scale data set, an annotated large-scale Sentinel-2 dataset for the detection of floating targets, and run a deep learning network to learn and detect the shapes of the targets, decipher the different components of the floating objects, and develop a tool or a platform for the users to spot floating objects, which could also act as an alert system for ocean cleanup activities. So next slide, please. Here, I'm going to show you some examples of our data set and also the results. So we have 6 representations: the RGB image, the NDVI and FDI, which are indices based on spectral information, the hand labeled image, and then the predictions and classifications with the neural network. And we see that visually speaking, the neural network learned quite efficiently the spatial patterns and managed to detect them. And quantitatively speaking, our method, which is the last row of the table, presents competitive performances with respect to the state of the art. So the Sentinel-2 labeled dataset is available and free, of course, and also the weights of the learned networks are available. Thank you.
Hello, everyone. My name is Raquel Carmen. I'm presenting one of the projects that Antanesia, Nicola, and I are working on at the PhilLab, which concerns tropical cyclones. This project is also carried out in collaboration with EUMETSAT. Next slide. Because tropical cyclones are major natural hazards, their analysis and forecast is highly beneficial for policymaking and risk management. However, one of the most widely used techniques for tropical cyclone intensity analysis, called the Borak technique, remains largely subjective and dependent on analyst training. The image on the left shows examples of tropical cyclone patterns assigned to specific intensity numbers using this technique. In parallel, L-band radiometers such as ESA-SMOS or NASA-SMAP and ESA Sentinel-1 synthetic aperture radar currently provide direct estimates of the ocean surface wind speed, and we can take advantage of them. So building on this study explores a deep learning approach to tackle 4 challenges. The first is to detect the eye-center of tropical cyclones. The second is to yield reliable estimates of their intensity based solely on the topology patterns, that is on the sea surface wind and rain-related patterns. The third is to provide explainability on the categorization. And the fourth is to locate the center of the eye, as it is then used to determine specific information for geographical storm quadrant. Using high resolution SAR data from the Sentinel-1 and also from the L-band radiometers, we are exploring the use of state-of-the-art convolutional neural networks such as ResNet-50 and MobileNet V2, pre-trained on ImageNet for the detection and categorization tasks, and region-based CNNs or YOLO for the localization of the eye center. Moreover, this study addresses the explainable AI field by applying gradient-based class activation maps to better understand the characteristics of the learning model. So far, we've achieved really good results on the detection with an accuracy of 97% and satisfactory performance on the categorization. Here I present a confusion matrix from ResNet-50 on the categorization task, where the predicted labels roughly fall under or around the diagonal, although some categories seem to be very difficult to estimate, and the quality of these results is mainly due to the amount of data that we are using for training, which is quite scarce for a deep learning approach. As you can see from the image on the left, upper left, the gradient-based class activation map successfully highlights key features of the tropical cyclone, namely the eye in the inner core region and the rain bands on the outer core. And as for future directions, we plan on implementing the eye center localization task, the augmentation of the data sets, and test another deep learning, machine learning approach like few-shot learning. Thank you very much.
Thank you. Hi, am I heard? I'm not sure. Thank you, Alex. So I'm Athanasia Nicolaou. I used to study magma oceans for exoplanets, and here I'm working with Raquel Carmel, that just spoke, on detecting atmospheric convective events over the ocean, but the water ocean this time. Detection and prediction. So first of all, the problem. The problem is thermally driven convection. So there is a temperature difference that between the vertical boundaries of the atmosphere and the boundary layer, the top of the boundary layer, and the surface of the sea causes buoyant upward air motion. Therefore we have the convection. It develops very fast, and it can lead, depending on the water content of the atmosphere, could lead to rapid precipitation. These are the events we want to map and to predict. And for that, we need geostationary observations, as well as very high resolution models, numerical models that resolve the motion in physical principles. I'm talking, of course, about the Navier-Stokes equations and the whole machinery that goes behind weather prediction. However, what we want to do here is to manage to diminish the time that is needed to calculate this by training a physics simulator that is going to imitate the process in a wider Earth model. So regarding the observational dataset, we classify clouds into deep convective and stratiform types. So that would be cumulus texture and stratus texture, in order to choose a suitable training for each. From the datasets that include convection, we use AI methods to cluster the events, and using genetic algorithms, we can compare them against additional methods from the literature. Regarding the model runs, of course, we need a wide volume of synthetic made data for that, And to do that, we're using simplified setups, but are non-hydrostatic, of the Rayleigh-Bernard thermally driven convection. From this, we select test cases of events that are taken are captured by observations, and we combine model data and observation data sets to evaluate the quality of the predictions for the places where the ground truth is missing. And that for us is the interest, next slide please, for oven ship routes. Thank you very much. I thought there was another slide for the shipping routes, but that's actually our main application to predict the weather of convective events over mid-ocean shipping routes. Thank you.
So hello, everyone. This project is about combination of air pollution and environmental health applications. So here I'm going to show you just an example how we reconstruct the NO2 using satellite and satellite-based data and AI algorithms. So the idea of this project is try to solve one of the historical environmental health problem, which is when you need to assign what is the exposure to people around at many locations. They usually use data from air quality monitors placed on the ground. But as you can see in this image, we have a very strong clusterization of these air quality monitors focused on main cities. And in this case, you still have on the picture in the middle, you can see some, let's say, synthetic data with the health outcomes. And when we overlap both, you see that there are a lot of gaps where we have people living, but we don't have information about how much they are exposed to a specific pollutant. And we already know that the pollution is a dangerous exposure to human health for a variety of health outcomes. So in the next slide, you can show the beauty, let's say, of Copernicus in this specific topic, because we are able to reconstruct the exposure at human level, the area that we are interested using the Copernicus data. So we can use data from climate change services, the atmosphere services, and also the land monitoring information, and also direct informations from Sentinel-5P, in this case that we are extracting NO2, but also different proxies such as NEDVI. And interesting here that we can combine this information and extract what is the concentration of a specific pollutant at the area that we are interested. In this case is the human level, the surface level. So in the next slide, is an example what have been already applied for PM2.5 and now is the next step. So this is an example of a specific place where we are doing that, but of course this can be replicable in other areas across Europe and also worldwide. So as you can see on the picture on the map on the left show the problem. The areas where you have exposure, information from pollution, and then we combine all these information from satellites and satellite-based data as our predictors and proxy for the potential reconstruction of air pollution, and we combine this with multiple machine learning architectures in this case, and we use more than one. In this case, as an ensemble, because we already know that air pollution is very different from one area to another, and some machine learning algorithms are very good to understand specific behaviors of pollution, for example, seasonality or winter, summertime, and then we need to give to another learning strategy to pick up other signals from that exposure behavior. So in here you see on the right, the colorful map is what we aimed, is reconstructing in the whole area what is the exposure for the population, and doing this reconstruction back in time, so the last 10 years, then we can give to the environmental health researchers this information. And in the next slide, I show you an example of AI for EO for health applications, that you combine this information with different health outcomes, and now you're able to give to every single part of your location of interest this information to linked, and trying to understand what is the association with mortality, hospital admissions, and specific health outcomes for that. And another interesting application is the policy in this case, that you also can analyze where are the areas where the concentrations of pollution is above a specific limit. In this case could be the European Commission air quality guidelines, but at the same time analyzing the World Health Organization limits in this case, and trying to understand what are the areas that is above or below these specific limits. And that's it for me. Thank you.
Hi everyone, I'm Alistair Francis, or Ali. I'm a research fellow here at the FELAB. I joined last month. So I'm going to show you some of the plans for the project that I'll be working on hyperspectral data, and also some of the results from my PhD work which relate to this. Okay, so the big problem in remote sensing when it comes to supervised learning tasks is the amount of labeling time. So all across computer vision, labeling takes up a massive amount of time, but in remote sensing, especially because we have so many satellites with different sensor characteristics, that kind of in some way multiplies the amount of labeling we have to do. So the idea of this project is really to make deep learning models that work across multiple satellites without any retraining, and also work on satellites that that it hasn't seen in training. So in that sort of with that aim, along that way, there'll be data sets created in hyperspectral for cloud masking. So as James Wheeler mentioned, there's a tool called Iris, which allows us to do semi-automated annotation of images. And the idea will be to label cloud and cloud shadows in hyperspectral data and release a large AI-ready data set for hyperspectral imagery and cloud masking. And really, the idea is that cloud masking is sort of one example of this approach, but the model architectures are problem ambiguous and could be used on a range of other supervised Earth observation problems. Next slide. Okay, so here's a few results from a previous study just on multispectral rather than hyperspectral. So you can see on the left here, the same cloud mask, which was trained on Sentinel-2 and Landsat-8 data, working on 4 different satellites. And the way it does that is that there's this novel neural network, which I won't go into the details of how it actually works, called Sensei. And the idea is that actually it can ingest any combination of spectral bands that you give it, and then it represents that combination of spectral bands in some shared representation that a single deep learning model can then use regardless of the bands that you gave it. So one more click will give us a big figure that I thought might be of more interest to EUMETSAT. Kevin, if you could just click once more. Oh, It doesn't. Okay, go back for a second. Okay, well, anyway, I just wanted to highlight that even though it's trained on Sentinel-2 and Landsat 8, it actually works really, really well on Sentinel-3. So we didn't have any labeled data for Sentinel-3, but it can produce pretty good cloud mass, even though Sentinel-3 is a sort of order of magnitude different in resolution. So we think that's a really promising result. Yeah.
So good morning, everyone. I'm Gabriele Meoni, and today we will present the use of neuromorphic computing for Earth observation applications. So we started this work by reviewing the deep learning and particular artificial neural networks used for Earth observation application, and in particular their advantages, their capability to scale to really complex model that made them the state of the art for many applications, especially in computer vision and natural language processing. But one main limitation of artificial neural networks, in addition to the limited biological plausibility, is the fact they are really computational intensive, and that leads to high power consumption. That's of course a huge problem, especially if you consider small CubeSat and onboard applications, especially if you consider that deep neural network models and their requirements double every 3-4 months in terms of energy. So one of the alternatives that we are considering is the use of spiking neural networks. So to understand why there might be advantages in terms of energy, try to consider the scheme that you find left when you have 3 neurons, A, B, that fires and provides some spikes, as the name says, to the neuron C. So A fires a spike in an instant. This is completely unrelated to the one B fires, and the voltage of C basically is the voltage V increases every time we receive a spike that is accumulated once it reaches a threshold VTH. After that, basically C fires the neuron itself. So as you can see, the paradigm of computation relies on not separation between memory and computation itself, and also really sparse due to the asynchronous and massively parallel approach is using. When deployed neuromorphic hardware, that leads to a lot of advantage in terms of energy that Andre will now present. Their main limitation is the fact, at the moment, the lack of maturity in this paradigm that might affect a bit of the accuracy of the paradigm itself.
Thank you, Gabriele. Good afternoon, everyone. So the motivations why we started looking at this technology, in particular for Earth observation, is that, as it was seen before, the deep learning actually contributes significantly to our CO2 emission because it's very power hungry. So while we're trying to solve certain problems related to, say, climate change, we are also directly contributing to them. So we need to find a new paradigm which can give us the same kind of intelligence capabilities, but is much more energy efficient. On the other hand, the advantage of it is that we are also looking at deployment of AI directly on board of small SATs. And there we inherently have a very limited power budget. So we need to find something which doesn't require a big energy consumption. So what we are currently doing in our research is trying to bridge this gap between the artificial neural networks and spiking neural networks. So we take an off-the-shelf deep neural network, which was trained on ImageNet on the cats and dogs that Pierre-Philippe was talking before, and we retrain it on Earth observation data. After doing that, we convert the neural network into a spiking neural network by taking all the activations of intermediate layers and converting them into spiking frequency. Then we fine-tune the network in order to reduce the number of spikes and hence to reduce the number of operations that we need to do, and by this reducing the energy consumption. While we do this, we try to keep the accuracy of the classification of land cover and land use as high as possible. And what we observe is that unfortunately we observe some accuracy drop, and this is because we need to stop the predictions at some point, and that means that some of the layers may not be saturated enough with the spiking information. But at the same time, we observe 34-fold increase of energy efficiency when we compare the standard application of a comparable ANN on GPU device versus the Intel's Loihi neuromorphic chip running a spiking neural network. You can find more details for this research following this QR code. Thank you.
Hello, everyone. I'm Dawood Erickson. I'll be talking about my work on 3D Earth models from multi-view satellite images. So the goal of this project is to take a set of images like the ones you see up here on the upper left of the screen and to create a 3D representation of the colors and of the shadows of the scene, with the final goal to be able to create new views. So what we call novel view synthesis of the scene from previously unseen viewing angles, but also under unseen lighting conditions, but also to be able to extract the depth or 3D map of the scene, and even to project it into a virtual reality environment using, for instance, a fast to render polygonal 3D surface model. So it was really groundbreaking in this work is to use the new paradigm of shadow neural radiance fields, which is an extension of the neural radiance fields, which came out last year, where we actually model the scene as a continuous parametric representation as a neural network itself. And this allows us to account for changes in lighting conditions, which previous stereo photogrammetry methods are not able to do. And a few applications are for rapid analysis after natural disasters, or for fusing together different sensors with different resolutions and revisiting our archives of satellite images. So go on. Here are a few results of this project. So on the top, you can see the ground truth image, which has never been seen yet by the network, as well as a LiDAR measurement, which represents the DEM or elevation of the scene as measured by an airborne sensor. And underneath are our results. So on the left side, it's basically when we do not model the shadows within the network. And there we can see that a lot of errors occur in the shaded areas, but also in the shape of the surface. But when we start modeling the shadows, as well as the contribution of the sky and sunlight separately, the shadows are far more accurately modeled, and the surface shape is also quite crisp and has a lower average error. And so one of the interesting side effects of this, or side products that we can get out of this learning, is that we can also remove the shadows from the representations. So to actually model in a way the albedo of the scene. And we can actually do this even on surfaces that are permanently in the shadows, like the facades of some of the buildings that are always shaded in the images. Thank you for your attention. That's it.
Hello everyone, so my name is Yoann Écuyer. I'm a research fellow here at FILABS, and I'm working on this project called Enhancing Sentinel View with AI Super Resolution. So in this project, what we are trying to do is to increase the spatial resolution of Sentinel-2. Sentinel-2 has several bands with several spatial resolution, and we are focusing on the RGB bands for now, which have a spatial resolution of 10 meters. And what we want to do is try to increase the spatial resolution to 2.5 meters. So on the left, you have an example of what an image of Sentinel-2 looks like. And the same for the same place, an image taken with a very high resolution satellites. We're working on a method that takes as input several images, and so which means that we are using several revisit of satellites over the same place to super resolve. The assumption is that we think that bringing more information will help to constrain the super resolution. But over several revisits, there is changes that can appear in the scene, such as seasonal effect, weather effects, or human activities. So we are working with a dataset that contains a little bit more than 100 areas of interest with different dynamic changes. And we are building our method on top of this architecture called IRISNet, developed by FDL. And we are in collaboration, working in collaboration with them to try to improve this result. Here you can see some results we have so far without taking into account any dynamic changes in the scene. And so you have on the left the low resolution image, on the middle the high resolution we are trying to reach, and on the right the super resolution resulting from our method. And you can see that for the first row, the result is pretty good, like it's very it's almost matched the high resolution image. But for the second result, what you can see is that the super resolution is very dark and blurry. And for this particular area of interest, we have a very few revisits available, and there is a lot of changes in the vegetation. And when you try to combine all those images, you have this kind of very noisy results. And that's why we are focusing on this part of the pipeline. And that's it for this project. And for the presentation of the research fellow. So if you have any question for us, we are open. Thank you very much.
Thanks a lot. I think that was the last. So we move to the question time. And while we wait, okay, so we have already a question. So in the multispectral cross-matching problem, would you consider using bias and inference based on a deep learning model library? I don't know who would like to answer this question.
Okay, if nobody does, I will, or at least I will try to bring some elements. There is a lot of techniques out there, and Bayesian inference is certainly something we want to look at, in particular to deal with uncertainty. So if this person, because I cannot see the name, could get in touch with us, we would love to explore this further together.
Okay, a question I have on my side is when Pierre-Philippe, you mentioned the possibility to actually, not the possibility, that has been already explored to have a GPU or on a CubeSat. Now the question would be, what are the drivers to, so how do you see, or what, from your perspective, are the main drivers for the future? So to operationalize, to better operationalize the development of products, to reduce latency, to reduce the increased security, to reduce the amount of data we transfer. So while transferring the full raw data, we transfer just L1 or L2 data level. So what are the main, from an operational perspective, what are the main drivers you see to have a full GPU system with the AI application and other algorithm application on space?
Okay, that's a question, in fact, that many people ask, because this is the question about why we should do that at all. Why don't we get all this infrastructure on Earth and do the job here? Why do we need to go up there and do things? And there could be a variety of answers, which, by the way, can change in times according to capability or interest of application. The initial thought was about data compression, so just downloading what is relevant. This is what the FISAT has done. It has done an intelligent discarding of images to understand which images could be downloaded, which is the one without cloud. So this is a kind of bandwidth issue. And some engineer would challenge you on this, saying that bandwidth will not be a problem anymore because you just need to scale the ground station. And there again, there might be questions about if you can do that, because the volume of data is growing much more rapidly than the bandwidth of telecom. Then there is the argument of latency. Some user would like to have information within minutes. So why not extract information on board and just send an SMS as soon as you have it through Iridium, through a radio, whatever the scheme, but it can go directly onto the phone of this person. And that would in fact bypass the whole processing chain, internet, the ground segment, and go straight to the guy who needs to make the decision within minutes. This is really powerful also because when you have IoT coming into the equations, IoT is basically measuring things in situ, like in Africa, and then sending it up and then down. So why not putting IoT and EO together up there and trying to create some products? So these are the main drivers, but the thing that is really driving me, at least personally, is another one, is the ability of agility of the machine learning that would enable you to have software-defined sensors that can change around the orbit, change according to needs. So it's really a Swiss knife. So this might not be for monitoring mission where you need always consistency of information. But for business mission or for application mission, where around the orbit you can have monitoring of very specific species of tree and then very specific type of sea ice, then the machine learning would offer this kind of configuration and flexibility. I mean, people talk about agility these days. So this trend is actually coming. It happened with a telecom mission that is now software defined. And I'm expecting that it will come more and more, in particular because the computing is coming and would be working in space and would be cheap.
Thanks for the perspective. I think maybe we can have time for a very last question, if any. Otherwise, I have probably one. I don't know, Regina. Otherwise, I think from a Philab perspective, you are actually exploring a bit of the interest of the market in some way. So you are looking to what are the requirements, and also from the Philab perspective, how do you see the development of small, medium enterprises that they are working around this area of downstream applications and looking directly to satellite data to derive products? So to jump a bit, a kind of shortcut from the traditional value chain where you have data, observations, data modeling, and then products, while now you can shortcut from satellite to products in many applications.
Okay, maybe I will take this one as well, and then I'll pass to the team. But this is really a kind of golden age for this entrepreneur. So the barrier to entry to our domain are going down. They just see space as a kind of data layer. So we can see that there is a big wave of AI, let's say, companies trying to have a go at this data. And we try also in the Philab and in ESA in general to stimulate this. That's why we do presentation like this. We have programs like InCube, which is managed by the Philab, to have these commercial angles. And what we notice is that the intersection of AI experts and domain experts really creates new services. And we have witnessed this at the Phi Week recently. We see this in conferences for digital entrepreneurship. So space becomes another data layer. And as you know, the money is in the information. So these guys are really bringing new techniques to our domain that our traditional community was not looking at, to really make the most of this. Generative model is just one example, the thing that Andrea Stockholm was talking about. This was extremely remote from us, then it's coming to us. There are also techniques that are not there yet, like reinforcement learning, etc. We don't have a lot of use cases, but what I can see is there is a community out there. We will need to raise awareness. The AI guys do not know that there are 15 petabytes of open data on the state of the planet. But when they realize that, they go banana and very excited because they can make an impact on sustainability of the planet with their tools.
We have 2 more questions.
Okay, let's see. So are there any plans to test in space existing hybrid electronic with the quantum components? That is one question. And could you give some script example for data processing? I think this one has been answered, the second one into the chat. So I think the first question, are there any plan to test in space existing hybrid? I don't know if there's a possibility someone to answer, or we.
Okay, I think it's a very technical question we can answer separately, but there is clearly plan to put different type of computing in space. It can go neuromorphic, TPU, VPU, possibly quantum computer. We don't know yet. The Moore's law is kicking up, and we have Gabriele and Andrzej looking at this in our lab. So I invite the person asking the questions to get in touch with them.
Okay, so with this, we can conclude. So thank you so much to Pierre-Philippe, Dario, James, Andreas, Yamila, Raquel, Athanasia, Rochelle, Alistair, Gabriele, Andre, Dawa, and Gurvan. I hope I didn't forget anyone. So thanks a lot again. See you soon.
Thank you very much, and reach us on the PhilAb website and on LinkedIn. Looking forward.
Thanks, everyone.
Bye-bye.
Bye.
Thank you very much.
Thank you. Bye.
Bye-bye.